Hey friends, we've reached the end of chapter 3. We're looking at section 3.5 and we're going to be talking about solving systems of equations in three variables. So remember when we started off solving systems of equations in two variables? We used the analogy of a line, like we recognized that it was linear equations. We were finding the intersection. When we're dealing with three variables, it's a little bit harder because three variables or three variable equations refer to a plane. So here's one situation here where three planes intersect in a point. This is the one we'll be looking for that we'll be able to solve. Then sometimes we'll find that the three planes intersect in a line where there's not one specific solution, but infinitely many. Sometimes we'll have no solution at all, where all three planes could do something like this, where they don't actually all three intersect. So, full disclosure, these problems are not hard, but they are tedious and time consuming. So, I actually solved this incorrectly and I'm doing it again. And it's not so much that I can't solve it, but it's that if you make one little mistake, everything else falls apart. So, you have to be careful. So, I'm telling you that so we can think through what's going to be best for us as we solve the problem. So, what you have to do when you're solving these types of problems is we're going to make them into systems of equations with only two variables. So first thing we got to do is get rid of one. So if I choose to get rid of a variable, it has to be either x, y, or z. I just look at the problem and I decide which one is easiest for me to do. And it looks like it might be easy for me to get rid of x. So what I'll do is I'll grab these two equations and I'll get rid of x. And I'll grab these two equations and I'll get rid of x. So I'll show you what I mean. First thing I'm going to do is get rid of x by elimination method. So that means I'm going to multiply this whole equation by -2 and then add it to this one, because then the coefficient of the x's will be additive inverse. Okay, so you guys see we get these two equations, which is just a repeat of this second equation. This first equation has been multiplied by -2 that I indicated there, and I'm going to add these two equations and watch what happens. X goes away. I'm left with -5y plus z, plus 1z, right, is going to be equal to a -25. I'm going to do the same thing here, but this time again, I'm going to be consistent. I'm going to get rid of my x term, but here I'm going to have to maybe multiply one of these equations by -1. Let's do this second equation. I'm going to multiply this guy by a -1, and after I do that, I'm going to rewrite it and add them together. Check it out. Now that that's done, I have additive inverses here. I feel comfortable with that. I'm going to add them together. These guys go away. These guys become a -2y, right? And a -8z. And when I add 27 plus 5, I get 32. So I have this as 32. Look at this. I've got two variables, two equations. I'm going to solve it. You know this. So I need to choose to get rid of one of my variables. Z looks the easiest because we've got a coefficient of 1 here. So I'm going to multiply this equation by a +8 on both sides. And then I'll do a rewrite and then we'll add. So I wrote this kind of tiny and small, but you guys can see that I get a -40y plus 8z is equal to -200. This is really what I was looking for, making sure that I had additive inverses here. So I end up with a -42y, these guys are gone, is equal to a let's see, 200 minus 32 is going to be -168, I believe, right? You guys will let me know if I'm wrong. And so we're going to divide both sides by that -42. And when we do that, we get that y is equal to a +4. That's cool, but now we got to solve for the rest. So now I'm going to take this y and I'm going to put it back into one of these equations where y and another variable is. If I were to put it back into one of the equations with the other two variables, it's not going to work out really well. I won't naturally get an answer. So I like to kind of do like this backstepping thing where I take what I have and I use it to get what I want. So I'm going to use this very equation here. -2 times 4 minus 8 times z is equal to 32. So then I get a -8 is equal to 8, -8 minus 8z is equal to 32. Moving the 32 onto the other side, I end up with a positive 40, so z is equal to negative 5 if I divide both sides by that negative 8. Now that I've nailed down y and z, I'm going to go back to one of the original equations and get x. So the equation x plus 2y plus z equaling 10 appeals to me. Any one of the equations would have been okay. So then x plus 2 times 4, notice I'm replacing y with 4, plus z, which is negative 5, is equal to 10. So I end up with x plus 8 plus negative 5 equals 10. These guys come together to give me a positive 3. X plus 3 is equal to 10. And finally, x is equal to a positive 7. So my answer, which I would write as an ordered pair or an ordered triple, would be written in XYZ form, and therefore my answer is going to be 7, 4, negative 5. That last example showed us what it would be like if we got a point as an answer. Now we're going to see what it's like if we get infinite solutions. And if you remember the diagram, infinite solutions meant we had a line where all of the planes intersected in a line. Process is the same. We got to decide on a variable to get rid of. And I'm going to get rid of, I don't know, which one looks easiest to you guys? I don't know, all of them look a little tricky. Let's deal with z. Let's get rid of z in each equation. Oh, let's get rid of x. I'm sorry, I just changed it because I was like, I don't feel like, well, let's get rid of z. I'm going back. I'm being tough. So we're going to get rid of z, and I'm going to stay there. And so let's take these first two equations, and then I can take these two just to be different. So if I take the first two equations, and then what I'm going to do to get rid of z is I need to multiply this top equation by, let's say, a positive 3 and multiply this second equation by a negative 2. And I'll write that down just to keep it in mind for me. So I'm going to multiply this top one by a positive 3. I'll get a positive 12. Multiply this by a negative 2. I'll get a negative 12, and then they'll cancel out. So already, as I multiply these guys just to eliminate the z, I realize everything is going to go away when I do that, which is not really a major problem. It just lets me know that something fishy is going on. So when I add up everything, all of it goes away, and I end up with 0 equals 0. If you remember from a previous video, when you get the same thing on both sides, this is a true statement, but it's not helpful. And so this lets me know that I'm dealing with something that is either, well, that's the same. I'm dealing with the same plane. And if we were to reduce or factor on both sides and reduce these equations, we would see that we got the same equations ultimately. But that's all right. I'm going to still push on with this problem. Remember, I wanted to use these two equations. And the reason why I'm pushing on is because you may have started the problem looking at a different pair of equations that didn't cancel out very nicely. So let's see what happens here. If I need to get rid of the the z, the 4 and the 10 need to become the same thing. I'm going to change them to 20. All right, so what that means is I want a positive 20 here, maybe a negative 20 here. So I'm going to multiply this equation by negative 2, and I'll multiply this first equation by a positive 5, right? And so now let's see what happens. I'm going to give you guys the shortened version. So these are the resulting equations, and you can see they're not going to cancel out as nicely. So let's go ahead and keep moving and see what we get. So now we end up with these guys become 10x, right? These guys will become a negative 14y, and these guys go away, which is what we expected, and this is going to be equal to a positive 8. So now there's nothing else for me to work with. I'm just left with this xy equation, this linear equation, this line, right? And so infinitely many solutions, there's infinitely many xy points that are going to solve this, and it looks like the z value is irrelevant. So the xy, as long as the xy agrees, that's where our line's going to be, and we don't need to worry about it. Infinitely many solutions looks like we'll end up with a line that we can't resolve. Here in example 3, we have a no solution situation. So I think I'm going to just see if we can work through this problem as quickly as possible. Let's get rid of the B term because all of those are even. It looks like we might be able to do something fun. So I will take these two and then I'll take, I don't know, these two. All right. So I'll take the first and the third, and then I will take the second and third. So if I want to use the first and the third equation to get rid of B, I'm getting rid of B, I'm going to have to come up with a common coefficient here that I can make additive inverses. And the value that I think I'm going to use is 24 because 8 goes into 12, 8 goes into 24, and so does 12. And I am going to multiply this equation by a negative 2, and this one I'll multiply by a positive 3. So here are the resultant equations that I get, and let's see what happens when I add. Well, when I add these guys, the A goes away. I guess that's a benefit, right? When I add these guys, the B goes away, which was the plan. And when I add these guys together, I get a negative 5C. Are you guys with me? And when I add these guys together, the 48 goes away, and I get a positive 30. So that was kind of nice. I was able to get C pretty quickly, and C is equal to a negative 6 if I divide both sides by a negative 5. All right, let's see what happens here. If I take, which ones did I say? I said I'd take these last two. If I take these last two, again, I'm trying to get rid of B. What should I make this become? I think I'm going to make these 72, positive 72 and a negative 72. So positive 72 by multiplying by 4, and a negative 72 for this one by multiplying by negative 9. Okay, so this is what happens when we multiply it out. And look, weirdly enough, the A also falls apart, leaves, and so does B. And then here we're left with a negative 15C, or positive 15C rather. And then when I subtract these guys, let's see, what do we get? So check this out. When I divide 15 into this value, see, 15, no, this isn't going to work. I end up with a negative 7.6. This is showing me that I'm getting these two different answers. This doesn't even make sense. There is no solution. So I'm getting two different answers for the same variable, no information on the other variables, no way to seem to get any kind of information on the other variables. This is a no solution situation. I also want to show the way that the textbook authors did this problem to see that there was no solution. So they chose a different pair of equations to deal with. Notice they chose to deal with this first equation and the second equation, and we didn't do that. And when you did that, if you did that, you would have gotten a lie, like we have with our two variable equations when we were dealing with systems of linear equations. So I do want you to observe that depending on the two that you choose, you might get something that looks suspicious, as we did with ours. Let me go back to our screen. As we did with ours, at first it was just suspicious that everything fell out, and then we were left with C value, but here everything fell out again and we were left with a different C value. So that's our lie. We could have come up with the lie quicker if we had chosen the first and second equation. All right, so let's look at example 4. Now that you know how to solve three equation situations, doing them with word problems, the only hard thing here is setting up the word problem. So I'm going to set up this word problem, and I might have a part 2 where we look at some other ones like this. So let's talk about this guy. Take a second, read this, pause me, and then we'll talk. I hope you're done. I know I didn't want to take the time to read it now because it's going to take us a long time. So let's let A be the amount of money that he invests in the 1-year CD, B be the amount of money he invests in the 2-year CD, and C in the 3-year CD. Since he has $15,000, all of that money must add up to $15,000. This line highlighted in purple, along with this information, gives me the following equation. So this equation came from the idea that you're getting 3.4% on the A money, 5% on the B money, 6% on the C money, and we want it to all add up to 800. Here's our third equation. So this Green line here, he wants to put $1,000 more in the 2-year CD than in the 1-year CD. Okay, so I had to switch that. $1,000 more in the 2-year CD than the 1-year CD means that B is going to be